So we showed that whenever S was a finite set, we could say that the power set of S was going to be larger than S itself. But things got a little bit more complicated. We wanted to show this for all sets in general, not just the finite ones. If we wanted to show it for the infinite ones as well. This is going to be a much more complicated proof, and in fact, this proof was sort of so groundbreaking and revolutionary when it first came out that it changed how people thought about math in general. So prior to this proof coming out, everybody just sort of assumed that infinite sets were infinite sets, they were all the same size. What we're actually going to show is that even when S was an infinite set, its power set is larger, essentially saying that there are some infinities that are going to be larger than other infinities. This proof, as we go over it, is going to be a bit uncomfortable, and it should be, because it sort of changes the way that you're going to be thinking about math, and it was uncomfortable to expert mathematicians when they first heard it. So this proof was first presented by this mathematician named Cantor, so it's often called Cantor's proof, and it's going to be a proof by contradiction. So we're going to show that for all sets, the power set of S is larger than S, and we're going to show this by contradiction. So our proof is going to be by contradiction. So that means, since we're showing this proof by contradiction, we're going to start by assuming the opposite of this statement here. So we're going to assume that the power set of S, the size of the power set of S is less than or equal to the size of S. So if the cardinality of the power set of S is less than or equal to the cardinality of S, then that must mean that there is some sort of onto mapping from S to the power set of S. So for example, that must mean that I can find some sort of mapping where the domain is going to be the set S, and the codomain is going to be the power set of S, and I can take elements from S and then map them to elements from the power set of S. So for instance, maybe I could have the set 3 as an element of S, and then that is going to map to some subset of S, which maybe that'll map to the set containing 2, the set containing 4, and 7. So maybe that'll map to 2, 4, 7. Or maybe what I have is the element 5, and that's going to map to this other element here from the power set of S, which maybe will be 3, 5, 7, or something like that. So if the power set of S is smaller than S, I need to be able to find a mapping like this that's going to be an onto mapping, meaning that everything over here receives an arrow. So let's call G such a function. So we're going to say let G be a function that maps S to the power set of S, such that G is onto. So since G is onto, that means that no matter what element from the power set of S we might look at, so for any subset of S we might look at, we're going to be able to find some element of S that's going to map to that subset of S. So for example, let's consider this other subset. I'm going to call it P. P is going to be all the elements, let's call them A, from the set S, such that A is not an element of the set which A maps to from G. Okay, so this is a little bit complicated what we're looking at right here, so let's tease this apart carefully. So P, we definitely know, is going to be a subset of S. So P is only going to contain elements that are also elements of S. And the way that we define which elements are going to be in P is going to be all those that are not included in the set they map to. So G, we said, maps elements of S to subsets of S. So that might mean that when we take the element from S, let's call that A, and the set that it maps to, G of A, it might be that A happens to belong to the set that it mapped to, or it might be that it doesn't. So for this example function up here, we have that 3 is going to map to 2, 4, 7. So in this case, 3 does not belong to the set that it maps to, whereas 5 maps to 3, 5, 7, so 5 does belong to the set that it maps to. So in this case, 3 would be an element of the set P, but 5 would not be an element of this set P. So P contains all of the things from S that don't belong to the set that they map to. So now, since P is a subset of S, it must be that P is an element of the power set of S. So since P is a subset of S and the power set of S is the set of all subsets of S, P must be one of the things in 2 to the S. So now we can say that since G is onto, there must be some X that belongs to S where G of X is going to be equal to P. So since we said that every element of the power set of S was mapped to by something from the set S by that function G, since G was onto, when we look at this set P that's an element of the power set of S, there must have been something from S that mapped to it. So let's call that thing X. So now we're going to ask this question, is X in P? And what we're going to see here is that we can't answer this question. Now, this is just a yes or no question, so the answer better be yes or no. Let's try to figure out what that answer is. So maybe it's yes. So let's say that the answer to this question is yes, X does belong to P. So if X belongs to P, then that implies, by the definition of P, that X does not belong to G of X. So P was the set of all things that don't belong in the set they map to. So if X belongs to P, then that means X does not belong to G of X. But G of X is equal to P, so X does not belong to P. So if X belonged to P, then we could conclude that X does not belong to P, so that doesn't work. We have a contradiction there where that doesn't work. So now let's try no. So if X does not belong to P, then that implies that X does belong to the thing that it maps to, because it was in the opposite of P, so P was the set of all things that are not in what they map to. So if X does not belong to P, it must have belonged to the thing that it mapped to. But once again, G of X is equal to P, so that means that X does belong to P. So if X doesn't belong to P, we must conclude that X does belong to P. So again, that's another contradiction. So what we see here is that if it was the case that the power set of S was smaller than S, or the same size as S, then we'd be able to find this surjective mapping. But when we look at this surjective mapping, we could use it to construct this set P that was impossible, because P couldn't have anything mapping to it. So what this proof shows us is that it's impossible for us to ever have a surjective mapping from S to the power set of S, allowing us to conclude that the power set of S must be larger, strictly larger than the set S, even if S was an infinite set. So now what we've seen is that regardless of whether the set was finite or infinite, the power set of some set is always going to be larger than the original set was. So when we look at the set of natural numbers, for instance, the power set of the natural numbers must be a larger set than the natural numbers was to begin with. So even though the set of natural numbers was an infinite set, the power set of the set of natural numbers was a larger infinite set in some sense. So now when we look at Python programs, we saw that the number of Python programs was countable. Its cardinality matched that of the natural numbers. But we can have sets that are so-called uncountable, where uncountable means that the size of the set is greater than that of the natural numbers. So when we're looking at can we actually implement every function with Python programs, we need to figure out what kind of infinite is the number of functions that we might have to implement. So if the number of functions is a larger infinity than the number of Python programs, we're not going to be able to implement all of those. So let's work on that. So we know the set of finite binary strings is countable. But what about the set of infinite binary strings? So what we're going to show next is that that set is uncountable. So if we want to consider all the binary strings that are of infinite length, we want to show that's uncountable, namely that the cardinality of that set is greater than that of the natural numbers. So uncountable means its cardinality is greater than the cardinality of the natural numbers. So the way that we're going to prove this is using a special kind of proof by contradiction that we often call diagonalization. And we're going to see why that's called diagonalization. So the way that this works is we say, assume, toward a contradiction, that the set of infinite binary strings was countable. So in this case, if it's countable, then that means we're going to be able to have a bijection between these two sets. So we should be able to find a bijection between the natural numbers and the set of infinite binary strings. Now you can think of a bijection between the natural numbers and some set as a way of listing all of the elements of that other set. So when we look at this bijection, we would say that the thing that maps to 0 is going to be the first thing in the list. The thing mapping to 1 is going to be the second thing. The thing mapping to 2 is going to be the third thing, and so forth. So if this is a countable set, we should be able to provide a list of all of the elements that are in the set. So what we're going to do in order to show that this set is not countable is we're going to show that no such list of elements can exist. So this is how this list might look. So in this list, we're going to say that each row is going to be one of our infinite binary strings. We're going to have the first row is going to be whatever 0 is associated with, the second row is whatever 1 is associated with, and so on. And then we're going to list all of our infinitely many bits in the columns. So the first column is going to be the first bit of our string, the second column is going to be the second bit of our string, and so forth. So what we want is we want to make it so that every single infinite binary string is going to appear somewhere on this list. So everyone is going to be a row somewhere. So maybe row 0 is just going to be the string that has all zeros in it. And then maybe row 1 is going to be all ones in it. Then maybe we can alternate zeros and ones. So every string is going to appear somewhere on this list. If we have a bijection, then that is definitely going to be the case. So what we can do to find our contradiction is we can show that no matter how we might try to construct this list of all of the infinite binary strings, we're always going to be able to find something missing from the list, thereby showing us that it's impossible to have a complete list, so this bijection cannot exist. So the way we're going to do this, and this is where diagonalization comes from, is we're going to use this hypothetical list that we're trying to show doesn't exist in order to construct something that is impossible to appear on that list. So the way we're going to do this is let's look at binary string 0. And we're going to look at bit 0 of binary string 0. So we're going to find that there is this other binary string, let's call it S, that we can create by inverting bit 0 of string 0. So bit 0 for S is going to be a 1. And then we're going to invert bit 1 of string 1. So that's going to be a 0. And then we're going to invert bit 2 of string 2. So that's going to be another 0. And then we're going to invert bit 3 of string 3, another 0. We're going to invert bit 4 of string 4, that happens to be another 0. Bit 5 of string 5, that happens to be another 0. And we're going to define S to be the string that results from doing this for every single row in the column. So for all infinite choices of I, we're going to define bit I of S to be the inverse of bit I of string I in this list. So because of how we defined S, we know that S couldn't have been any of the things in the list. Because if you told me, oh, S, yeah, that was actually in the list, it was going to be at row J, I could say, nope, not going to be on row J because it's different at bit J. So no matter what row in this list you picked, I'm always going to be able to show that it was different from the string at that row because I could find one bit where they disagreed. So now this shows us that we can't ever have a list of our infinite binary strings, which means we can't ever have this bijection between the natural numbers and the infinite binary strings. So we must conclude that since they're not equal, but they're both infinite, that the cardinality of the set of all infinite strings must have been greater than the cardinality of the natural numbers. So therefore, this is an uncountable set. So now we're going to show that all of the functions that are mapping strings to strings is actually an uncountable number. So the idea for how we're going to show this is we're going to use this proof where we demonstrated that the number of infinite length binary strings was uncountable. And we're going to take that set of infinite length binary strings and show that the size of that set must be less than or equal to the number of string-to-string functions. Now, to make it easier for us to show that the size of the set of infinite binary strings is less than the size of all the string-to-string functions, we're actually going to show that it's less than this slightly simpler set, which is all of the functions mapping strings to bits. So the idea for how we're going to show this is we're going to show that the number of string-to-string functions is uncountable by showing that the number of infinitely long binary strings is a smaller set than the number of functions that map strings to bits, which is a smaller set than the number of functions that map strings to strings in general. Now, before we get started with that proof, let's actually look at how we can represent a function. So the idea for how we're going to be working this proof is we're going to show that we can use these infinitely long strings to actually represent functions. So let's show how to do this. So we can think of functions as just kind of tables, where we have a table where you take your input and map it to the output. So in this case, our table says our input string is going to be in the left column, and then the bit it's going to map to is going to be in the right column. So since the number of strings is countable, we've shown this before, we can list all of the input strings in this column. So that's certainly doable. So now all we have to do is fill in next to that what is the bit we get as output if we were to apply our function to our input string. So let's, for instance, say that the function that we were going to be applying was this even length function. That is, it's going to return 1 if the length of the string is even, and 0 if the length of the string is odd. So in this case, when we look at our input, if we have the empty string as input, that is length 0, which is an even number, so our output bit is going to be 1. The string 0 is of length 1, which is odd. The string 1 is of length 1, which is odd, and then the next several strings are going to be of length 2, so we're going to return 1 for each of those. And then we have a bunch of strings of length 3, so we're going to return 0 for those, and then we're going to go to length 4, and so forth. And this is going to keep going for all of the infinitely many strings. So if we could potentially build this infinitely long table, we could represent this even length function. Similarly, we could look at this function of majority ones, which would have a slightly different table. This majority ones function says that the output bit is going to be a 1 if the majority of the bits of the input string were also 1s. So in this case, if we have the empty string, there are not more 1s than 0s in that string, so our output bit is going to be 0. If our string is just 0, we don't have more 1s than 0s, so output is 0. The string 1 has more 1s than it has 0s in it, so our output is 1. 0, 0 gives us 0. 0, 1 is half and half, not a majority, so we're going to get 0. 1, 0 is also 0, but now 1, 1 has a majority 1s, so we're going to get 1. 1, 0, 0 is majority 0. 1, 0, 1 has more 1s than 0s, so it is 1, 1, 0 and 1, 1, 1, and we can just keep going on forever and ever and ever with all of our infinitely many strings. So now something that we can look at here is that if we had agreed in advance what the order of our input strings were, we could represent all of the contents of this table with just the output column. So with just this right-hand column, we have all the information we would need to construct the table if we had an agreed upon order for our list. So that means that we should be able to represent any function mapping strings to bits by just an infinite binary string. So now back to this proof that the number of string-to-string functions is uncountable. So what we showed now is that infinite binary strings can represent functions, and functions can represent infinite binary strings. So because we have either set being able to represent the other, we can show that the cardinality of the set of all infinitely long binary strings must match that of the number of functions mapping finite binary strings to either 0 or 1. And since we knew that this was uncountable, So is that. And since the number of functions mapping binary strings to 0 and 1 is a subset of the number of functions mapping strings to strings in general, that means this set size is less than or equal to the number of string to string mappings, and so this is also uncountable. So let's just take a moment to appreciate a little bit what we've covered so far. So we've shown that Python programs can't compute every function. We don't know which particular functions Python isn't going to be able to compute, but we know that there's some of them out there. So we know this because there were a countable number of Python programs in general, but there were an uncountable number of functions that we might hope to implement. So because the number of functions is a larger set than the number of Python programs, we can't map Python programs to all of the functions. So there must be some that don't have any Python programs associated with them, and so they can't be implemented.